In this video, we're going to cover section 11.7 on the preparation and reactions of esters. Now recall that esters in the amides are less reactive carboxylic acid derivatives than acid chlorides and acid anhydrides. So what we will see in some of these examples is that we'll require either catalysts or heat to carry out these transformations. So let's first look at ways in which we can prepare esters. When treated with a strong base, followed by a primary alkyl halide, carboxylic acids can be converted into esters. As you can see, this is a two-step process. The first involves the carboxylic acid reacting with a strong base to form the carboxylate ion. That carboxylate ion then functions as a nucleophile and can react with a primary alkyl halide in an SN2 manner. So we carry out nucleophilic substitution to give you the ester. Now, another common method to convert carboxylic acids into esters is known as Fischer esterification. And in Fischer esterification, we take the carboxylic acid, we react it with the alcohol, which will eventually be that alkyl group of the ester, and we must carry out this reaction in the presence of an acid catalyst. So the net result of a carboxylic acid reacting with an alcohol in the presence of an acid catalyst is to produce the ester and a molecule of water. So let's look at this mechanism in a little bit more detail. Now, the Fischer esterification process is a little bit lengthier than what we've seen previously, but the same two core steps, the same two arrow pushing patterns that we've observed for nucleophilic acyl substitution are also important in this mechanism. They are the nucleophilic attack and loss of a leaving group. The only difference between this mechanism and what we've seen previously is that there's additional proton transfer steps. And so let's look at this one in more detail. So because we require that acid catalyst, the role of the acid catalyst is to protonate the alcohol. And so the protonated alcohol is shown here. So we have alcohol reacting with our acid catalyst to form the protonated alcohol. This ends up being the source of protons in that initial step. So we see that it's the oxygen of the carbonyl group that is going to pick up a proton to form this protonated carbonyl. This is a much better electrophile, and the reason why we need an acid catalyst. With acid chlorides and acid anhydrides, they're so reactive that they don't require any enhancement in their electrophilicity, whereas esters and amides, not being as good of electrophiles, they do require an acid catalyst to protonate the carbonyl oxygen such that we have a much better electrophile open to nucleophilic attack from the incoming alcohol. And so in that second step, we do have nucleophilic attack of methanol onto the carbonyl carbon, breaking of the pi bond. That leads us to this particular intermediate. In the next two successive proton transfers, the role here is to convert this species to a poorer leaving group and to make this hydroxyl group a better leaving group. And so the first step involves proton transfer to a molecule of methanol to form the protonated alcohol. Now the result of this proton transfer is taking this oxonium and making it neutral, making it less of a good leaving group. So the next step involves protonating this hydroxyl group to make it a potentially better leaving group. And so again, our protonated alcohol is our proton donor. That will protonate this hydroxyl group to give us an oxonium. It's now this species that with reformation of the pi bond of that original carbonyl and loss of a water molecule, we generate back a protonated carbonyl species. But now we have the ester functional group present in our structure. The final proton transfer step is to regenerate our catalyst. So a neutral molecule of the alcohol will pick up a proton from our protonated carbonyl, and that will form our ester. So again, this is a reversible process, meaning that if we increase the amount of water present in our reaction mixture, we can force the hydration of the ester back to the carboxylic acid. But if we can introduce copious amounts of an alcohol and ensure that we're removing water potentially from our reaction mixture through various distillation apparatus, we can produce the ester from that carboxylic acid. Now, as we saw previously, recall that if we start with an acid chloride and react it with an alcohol in the presence of pyridine, we can also produce the corresponding ester. Now let's look at some reactions of esters. So esters can be converted into carboxylic acids if we first treat the ester with sodium hydroxide and then follow that with an aqueous workup or an acid wash. Now this process is called saponification, and it's the main way in which we produce soap. So let's look at this mechanism in a little bit more detail. So saponification involves the following. Same two core steps that we saw for nucleophilic acyl substitution. We have nucleophilic attack of the hydroxide ion from our strong base onto the carbonyl carbon, breaking the pi bond to give us our oxide intermediate. Now the next step, the loss of the leaving group, involves the loss of a very strong base, the alkoxide. So this is a poor leaving group, but the reason why this reaction proceeds so efficiently is that this leaving group re-reacts with the newly formed carboxylic acid to give you the carboxylate and the corresponding alcohol. So in effect, this proton transfer locks in this reaction. If it weren't for this subsequent proton transfer occurring immediately following the formation of the carboxylic acid, the equilibrium would rarely favor this forward direction. So this reaction helps to ensure that we get overall completion and formation of the carboxylate ion. Now the second step of this reaction is conversion of the carboxylate to the carboxylic acid. And so a dilute acid is introduced to protonate the carboxylate to form that particular carboxylic acid. Now, as I mentioned, this is the main process for producing soap. We start with fat molecules that contain 3 ester functionalities, and under basic conditions, these ester moieties are hydrolyzed to give us carboxylates. So as you may know, how soap works is that the hydrophobic tails of those sodium carboxylates surround the nonpolar oily molecules by forming micelles. And the surface of the micelle is composed of those polar carboxylate groups, and that renders the micelle water soluble. And as a result, oily molecules are encapsulated in these micellar structures, and they are washed away down the drain. Now, as I mentioned, esters can also be hydrolyzed under acidic conditions back to the corresponding carboxylic acid. And this process is the reverse of Fischer esterification. So the mechanism for the hydrolysis of esters is the same as Fischer esterification. The first step involves a proton transfer to make the ester a better electrophile. And so we have a proton transfer between our ester and the hydronium ion to form the protonated ester. We have water acting as a nucleophile to form a new oxygen-carbon bond with the carbonyl carbon, and we break that pi bond to form this new intermediate. Now the next 2 subsequent proton transfers is really to set up this particular group as a better leaving group. And so first we have a proton transfer which removes a proton from this oxonium, water acting as the proton acceptor to give us back the hydronium ion. That generates a neutral species, which is then protonated using the hydronium again to form a protonated oxonium at that location. This now is set up to be a good leaving group. And so we have reformation of the carbonyl pi bond, and we lose a molecule of methanol. That gives us our protonated carboxylic acid and a final proton transfer, again, water being the base, picking up a proton from the protonated carboxylic acid to give us our neutral carboxylic acid. Now we can react esters slowly with amines to give amides. However, this process is generally considered impractical. And that's because it's much easier to make amides from acid chlorides using either ammonia, a primary, or secondary amine. Nonetheless, in the presence of ammonia, we could convert an ester to an amide, albeit it'll be a very slow process. Now recall that esters can also be reduced to alcohols using lithium aluminum hydride in a two-step process where we first react the ester with excess lithium aluminum hydride, and then we have a final proton transfer from a protic solvent like water to give us our primary alcohol. Now, if we wish to reduce the ester to the aldehyde, but not react the aldehyde further to the alcohol, we need to use a more selective hydride reducing agent. And this is going to be the last new reagent of the course. It's referred to as diisobutyl aluminum hydride. And similar to the lithium tri-T-butoxy aluminum hydride, we have bulky groups surrounding that aluminum center. So DIBAH is going to act as our hydride delivery agent, and it's going to produce, again, through a nucleophilic acyl substitution mechanism, it's going to produce that tetrahedral oxide intermediate, and then we're going to have subsequent reformation of the carbonyl and loss of the methoxide. And then in a second subsequent step, we will add water to react with the methoxide to form methanol, and that water can also be used to react with any remaining DIBAH. So again, this is a selective hydride reducing agent, and it's important to remember that this reagent only reacts with the esters relatively well, and the previous reagent is specific for acid chlorides. So although they carry out the same process, we normally use DIBAH for esters, and we use the lithium tri-T-butoxy aluminum hydride for acid chlorides. And lastly, we can treat esters with Grignard reagents and organolithiums to reduce these functional groups to the corresponding tertiary alcohol in much the same way we saw previously for acid anhydrides and acid chlorides. So although the esters are less reactive than the acid chlorides and acid anhydrides, the esters still have some synthetic utility. We saw that esters could be converted to the corresponding carboxylic acid in one of two ways. Starting now. Although esters are less reactive than acid chlorides and acid anhydrides, esters still are synthetically useful species. We saw that we could convert esters to carboxylic acids under acid catalyzed hydration conditions, or via a saponification process, where the ester first reacts with sodium hydroxide to form the carboxylate, and then with a subsequent acid wash, we can form the carboxylic acid. We also saw that we can convert the ester to the amide, although we mentioned that this reaction is quite slow, and that there's better ways to make amides, specifically from acid chlorides. And then finally, we looked at ways in which we can reduce esters to the corresponding alcohol using well-known lithium aluminum hydride conditions, but we introduced a new reagent in DIBAH, which will selectively reduce the ester to the aldehyde and proceed no further. And then finally, we saw that yes, we can use Grignard reagents or organolithiums to produce tertiary alcohols, which in effect is increasing the amount of carbon in our target molecule. And so if you have any questions about the preparation or reactions of esters, by all means, send me an email. Thank you.